welcome back. In this lesson, we're going to continue our discussion in the analysis and design of SRR beams. Now remember, SRR stands for singly reinforced rectangular beams. So they're rectangular cross sections with a single set of steel or group of steel. We don't have steel in compression, only in the tension phase. So as we start to set up for being able to analyze this, we're going to kind of spend some time today talking about the life of a concrete beam. These are all flexural analysis type of problems. They'll follow a similar procedure to what we've shown in previous videos. All right. Now, if you recall from your basic steel design class for structures, we often plotted a load versus deflection relationship for structures that met our assumptions of LEIH. Okay. And remember, LEIH is linear, elastic, isotropic, homogeneous material. So structures, such as steel, it worked pretty well. But in concrete, what we know is that concrete has some differences that occur to it throughout its life. Okay, and there's actually 3 different regions that we're going to kind of be considering in this. And so, because of these differences in concrete before and after cracking, we actually use something called a moment curvature diagram a lot of times to evaluate things such as ductility and overall behavior. And so that's what this lesson is going to be dealing with. All right, so we're going to define something called curvature instead. Okay, and it all comes back to how we set up our strain diagram. And basically what curvature is it's kind of a measure of this angle, if you will. It's not really an angle, but it's kind of the inclination of the strain diagram, right? Because remember, if there's no load on it, my strains are all 0, and then as I increase the load, this thing starts to kind of turn and rotate over. Okay, now if we keep our assumption of plane sections remaining plane, then this becomes a linear distribution. And so basically at any time, if I know the strain in the concrete at the top, I can find the corresponding strain in the steel. That will be a measure of the ductility. All right, and as I change the area of steel, that affects the stress, and the stress then affects the strain. So that's kind of how we can kind of profile the behavior of this beam. It's kind of a way of evaluating the effectiveness of a certain amount of steel. Okay, now for an uncracked section, if you look, remember we're always interested in the location of the neutral axis, and for uncracked or even cracked sections, this is the location where E is equal to 0. Okay, and that's the definition of our neutral axis. So if the section has remained uncracked, then this distance x that defines top fiber down to neutral axis, this was KD. Okay, but once I crack the section, the KD rules don't really apply. Okay, but I do need to know this value, whatever it is, and this becomes kind of the trick in figuring out curvature. All right, so what we're going to do is in this diagram, EC is the strain in the concrete, ES is the strain in the steel, and then the phi, that angle, if you will, is our curvature value. So from just a little bit of geometry, we can show then that the curvature of this is basically the strain in the concrete over the location of the neutral axis. Okay, this EC over X term, and that's what we're going to kind of work on today in this particular lesson. Okay, all right. So let's take this and kind of look at an example phi curve, if you will, phi being the Greek character that represents our curvature. Again, this is an SRR beam. This is rectangular. We have a width of 12 inches, a height of 24, and then my area of steel is 2.5 square inches. Now, I don't know whether that's number 3s or number 9s or whatever. It doesn't matter. My AS is 2.5 square inches. Okay, and so for this cross section, this is what our strain diagram looks like, is that we get kind of a strain in the concrete, we get our neutral axis, and then our strain in our steel, just like we pictured in the first diagram. Okay, and if I start this loading at the beam at a strain of 0 with no load on it, and I slowly increase the moment on this cross section, again, this thing starts to rotate over, and you get a curve that looks something similar. And then you'll notice that over the life of the beam, there are 3 distinct points that have to kind of show up. Okay, on this horizontal axis is my curvature, that's my phi value. And on this axis is my moment, that will be M. All right, and what we notice is as we increase the load, this diagram proceeds linearly up until the point of first cracking. Okay, and then once I crack, remember we said that we're going to neglect the tensile stresses in concrete for capacity, I get a little bit of a shift, and this curve changes a little bit. We get a kind of an immediate jump as the steel is activated, and it's not a very big jump, but it just kind of slides over a little bit, and then it proceeds on almost in a linear fashion, maybe not exactly, but pretty close in a linear fashion, up into the point in which the strain in the steel reaches its first yield value, okay? And so that's what we're calling as epsilon y, okay? And then once I yield, then all of a sudden, our steel isn't capable of carrying any more load, and so our deformations start to ramp up really, really fast. And so this becomes much, much more flat, much flatter. Now, we do get a little bit of a strain hardening effect, but we can kind of look at, the strains in the concrete that are a result. Now, if you remember, we said maximum strain in concrete was 0.003, but if I kind of plot this strain diagram without care of where it ends, this thing, I can continue this curve, but it remains reasonably flat coming across here. So that's one of the things that we want to kind of look at. Now, the usefulness of ductility is if I get a beam that only gets to here before it actually fails, okay, it hasn't deformed a whole lot, okay, versus one that gets way out here on the end of this thing, okay, this becomes a measure of what we call ductility, and ductility is good for ensuring that a beam, once it reaches a limit, it just doesn't, I hit this point and it just doesn't die on me, okay? Very important in, situations for, like seismic events and loadings in which I want a structure that will deform so that it just doesn't suddenly collapse, injuring people or rendering the structure completely useless. Okay, it affords us some time for people to get out and get to safety in the case of an emergency. But these are the 3 points: the cracking point, the yield point, and then whatever this ultimate over here ends up being. Okay, and so we're going to kind of study these three phenomena. Now, up to the cracking point, this is what we did in the last video with the elastic flexural stresses. Okay, so we want to kind of look at what's going on here. Okay, so let's take a look at some of the factors that are going to affect the moment curvature for us. Okay, and so we'll look at these. Okay, and what I've done is I've pulled some figures from some resources that kind of show the relationship of what's happening on this. Okay, and so what we're going to do in the curves that I'm going to show you is we're going to vary some of the value. Okay, so the primary variables that we kind of want to look at is I want to vary the area of the steel, I want to vary the yield stress, I want to vary the depth of the beam, F prime C, the compressive strength of the concrete, and then the width. And we'll show kind of what happens to these as we run the analysis and look at our moment curvature relationships. Okay, so what I've done is we've got our basic section that had an area of steel of 2.5, Fy 60, the depth 21.5, and F prime C 4,000, and then the width is 12. That's the picture that we showed on the last page. Okay, and then we kind of vary this a little bit, kind of do a kind of a parametric study. Okay, I do one with a moderate AS in which I go to 4.5 inches of steel and everything's the same. I go to one with a high area of steel, 6.5, everything else is the same. So all we're doing is changing the amount of steel and looking at what happens to curvature when I do that. Okay, and then another case that we'll look at is we go to a high Fy value, in which I go to 80 KSI, go to a larger D, in this case, that goes to 32.5. We go to a higher F prime C, so instead of 4,000, it goes to 6,000. But you'll notice we're only changing one parameter at a time as all it goes. And then we'll look at what happens with a large B when I go from 12 to 18, and we'll see kind of what happens on that. So let's start with the first one and look at the effect of the area of steel on the moment curvature diagram. Okay, now I know it's kind of hard to read, but it kind of illustrates the picture for the same beam, everything else being the same. If all I do is change the area of steel on this, you'll notice that the area of steel, for this lower line was that first case, the 2.5 inches squared, and the area of steel for our moderate value was 4.5, and then this is our area of steel for 6.5. And you'll notice that all things being equal, except for that area of steel, the behavior of the moment curvature diagram becomes very, very significant, right? Obviously, if I put more steel in it, it can hold a whole lot more load, but it also means that the strain isn't as much. It takes a lot more load to get the same equivalent strain as the strain I was getting on this guy. So by putting in a larger amount of steel, I don't get nearly as much ductility as I do this smaller amount. Okay, and so this will start to be something that we look at, from a design standpoint, that, if I'm trying to ensure ductility, I don't want to over reinforce a section, right? Because what happens is we're getting up to our cracking point, which is basically the same for all three pictures, and then we go up and we look at, in this case, this is where the steel yields, and then we had a whole lot of residual capacity, and you can see those 3 points start to show up. Here's the yield point for that moderate case, and you can see that it stays flat for a little while, but then it drops off fairly quick. But when I went up to this really high value, as soon as I cracked the section and I got up to roughly the yield point on this thing, it then just died off. I didn't get that horizontal projection. So basically, as soon as you yielded the steel, I had too much steel in it that basically I crushed the concrete first, and that's why it starts to die. So the general relationship is that as I increase my area of steel, again, we're looking at formulas that say sigma is equal to P over A, and then epsilon is equal to sigma over E, that if I increase A, I decrease the stress, which decreases the strain, okay? And you can see kind of what happens. Now, we know that as I add steel, I can increase moment capacity as a result of changing the AS value, but at the same time, this picture also shows me that I decrease the curvature. And so there's kind of this balance that we want. We want to be able to make sure that we have enough moment capacity to hold the loads, but at the same time, I want to ensure that I design this in such a way that I don't hurt the curvature or hurt the ductility of the structure. So it's kind of an interesting relationship that happens. And this is a phenomenon that we don't have in most standard steel beams per se. Okay, so let's take a look at what happens with some of the other parameters that came out of that table. All right, so I've got my Fy, my D, my F prime C, and my B, and we're going to look at what happens with the curve here. Okay, now if you look on this, again, the cracking point for all of these appears to be about the same value. Okay, although if you look, the cracking point on this first line is where we're increasing D. Okay, that the cracking point is a lot higher as a result, because again, sigma is equal to my over I, right? And so if my Y value has to go up, then the stress that goes up corresponding will correspond to a kind of a higher moment kind of value. So that's what we're looking at here. Okay, so if I kind of compare the values from the baseline, our basic line is this bottom guy right here. This is that same curve that we showed up on the first one. Okay, and so if I increase D on this, all we really do is we increase the moment capacity, but we don't gain anything in terms of the curvature, because we still end here and we still end here, and that's basically the same point that's happening on that. All right, now if I look at my increasing the Fy on my steel, that's kind of similar to increasing the area of steel. You can see that it now, I get a higher moment capacity for a set amount of a set amount of steel on there, but I don't get the extension or the ductility that I want. So it's kind of the same phenomenon that we saw back up here in figure 1. All right. Likewise, if I increase F prime C or increase the width of the section, okay, I don't get any increased moment capacity per se of this. I still reach the yield point at the same point, okay, but I do start picking up some extra increased ductility in our section here. So the basic relationships that come out of this general plot that we say is that as I increase Fy, the moment goes up, but the curvature goes down. Okay, if I increase D, the moment goes up. There's no real change in curvature. If I increase F prime C, no change in moment, but curvature goes up. If I increase B, no change in moment, curvature goes up. Okay, and that's kind of our general relationships that will exist between moments in the curvature diagram. So it's kind of an interesting little parametric study as we start to kind of look at that. All right, now we talked a little bit about ductility. Okay, and so basically what we're looking at is a measure of relative ductility can be achieved by measuring the area under the MV curve. So, and what that basically means is that if we assume that cracking and yield occur at the same point, the length of this line affects the total area underneath. All right, so if this is my ductility for a case, or this is Phi1, if I go beyond Phi1, everything else being the same, then this is said to be more ductile than this. It's almost like, it's kind of like the energy absorbing characteristics, or the analogy we like to use is if I have a bucket and I'm putting a bunch of water into it, okay, if I have a bigger bucket, I can put more water in it, okay, and where water would be the energy or the rotational capacity of the cross section. And so what we're doing is we're looking at these parameters as a way to increase my bucket size, if you will, on there. Okay, so that's kind of what ductility is. Now, the first one that we have is, if we go in and we're going to look at those 3 points kind of by themselves, the first point that we need to know is where is the cracking point. Okay, and what this is the point at which the stress at the extreme tension fiber is equal to that cracking stress. And since this is a flexural problem, a beam problem, this guy needs to be F prime R. It's that modulus of rigidity, or 7.5 root F prime C. Okay. Now, for positive moments, if you remember, for simply supported beams on here, a positive moment is a moment that causes cracking in the bottom, and a negative moment causes cracking in the top. And with that, we can start to kind of locate where crack patterns occur, and that will be one of the exercises that you'll do in one of the later assignments. It's fairly easy to kind of predict where those things are falling. Okay, now if we take our stress formula, and again, sigma equals my over I as a minus on this, all we're doing is we're taking this and kind of rearranging the behavior for our elastic stress. And we did this in the last example. Okay, our formula is that M is the applied moment, YT is the distance from the tension fiber to the neutral axis. So if this was my cross section and that's my neutral axis, if this is our stress block for sigma, then that's what we're calling as our YT. Okay, and so that's the nature of what we have here. Now, there's some dispute over what I value do I use. You can use the transform section if you want, but typically the moment of inertia for an uncracked section, we generally just use the gross area or the gross moment of inertia for this, just basically because the contribution of the steel in the section, if this is my steel, to the gross moment in a pre-crack state doesn't add much to the overall stiffness of the element. It's not until I crack it does this guy really start to kick in and play a much larger role. So if I plug in all the values that I have, I can write out the cracking moment. And this is really the moment right before cracking occurs, when we're still in an elastic section. Once my extreme tensile stress reaches 7.5 root F prime C, okay, I can rearrange all of this and I can calculate I know the section properties, and I can calculate this based off F prime C. I can figure out where that cracking moment is going to occur just from a simple plug and chug in my formula. Okay, all right. The second point on this is the yield point, okay? And this is what we call the first yield. Okay, it's the first location or the first strain at which my steel has started to yield. All right, now, again, we don't know epsilon C. From a design standpoint, I like that to be 0.003, but in a generic sense, I don't know this value, okay? But our yield point is defined as the time at which I have some strain in concrete that corresponds to the yield strain being equal to the stress or the strain in the steel. All right, so that this becomes my epsilon y. So remember that if Fy equals 60 ksi, our epsilon y is equal to 0.00207 inches per inch. And so it's just kind of, it's one specific diagram that exists in this. Now again, we're going to define some parameter x as being the distance from the top fiber to the neutral axis. This may or may not be kd. Okay, so we're just going to call it as x for now. Again, its depth goes from the top of the fiber down to the steel. That's this dimension. Okay, and then we basically go through and play that same game that we did with the elastic stress analysis, except now instead of being kd, we're calling this as x. Okay, the stress at the top is Fc. We still know that C res is located at the centroid of this triangle. Okay, because at yield, we're still assumed to be kind of an elastic behavior, assuming that we haven't cracked the, that we're still just it's a linear relationship is what we're assuming in this case. All right, so if this is x over 3. And then at this point, I know that my tension in my steel is, before we had said it was ASFS here, but now I've put the constraint on it that it has to yield, so now it becomes ASFY. Okay, and so it's basically the same basic picture as what we did with the elastic stress. Now, similar to the approach that we did in the elastic stress video, we can go through and we can calculate C res and T res. So C res is 1/2 of x times the stress in the concrete multiplied by B, and my T res is simply ASFY. Okay, and so all I'm going to do is I'm going to sum my forces, And so I know that for this particular picture, C res is the same as T res. Remember, the formula was minus C res plus T res all equals 0 is what we got out of statics. Okay, so that's all I'm doing here. And so I'm going to take this equation and set it equal to this one. And so ASFY is equal to 1/2 x times FC times B. Okay, now if we do make the assumption that x was our KD parameter from last time, okay, and assuming that it's still reasonably elastic up to the point at which the steel yields, it's kind of a, we got to be careful when we do that, but it's for an approximation for what we're doing. It's a kind of a good indicator of where that yield point occurs. I can find K from this formula that we derived last time. 2n rho minus n rho squared minus n rho. Okay, and then I can plug all of these parts into the formula. And remember, we said that we could calculate the moment of this by summing moments at this location, right? And so all I need is the distance from here to here. Well, that was my JD parameter, or it's the depth minus x over 3, okay? And then all I do is basically the only force acting on that system if I sum moments here is Ty. And so that's how we calculated the moment capacity, just like what we did last time. So my yield moment then is ASFY, and then D minus KD over 3 would be my yielding moment, the moment that causes yielding in the steel. It's not yielding of the concrete, but it's the moment that corresponds to the yield point, reaching the yield point in the steel. All right, so then once I have that value on here, if I set x equal to KD on the strain diagram, then again, that angle right there, that was my curvature, that was my phi. Okay, and so all I'm going to do is I'm going to take what would be, and if that's phi, then that angle is clearly phi. All I need is epsilon y, which we know, 0.00207 over that distance. Well, that's d minus x. Okay, and so that's where this formula comes from. So this KD guy right here, that was the x in my picture. And so I can calculate the corresponding yield curvature at the point when the steel yields to be epsilon y over d minus KD, and it becomes a very, very simple procedure for what we're doing to get the yield point. Okay, all right, so kind of walking you through the steps that you have to do. Again, for my students, this is one of the example handouts that we'll kind of work our way through. Okay, the information that we have might be a transformation ratio, a grade 60 reinforcement, a 1/2 inch of bottom cover. Now, this bottom cover is basically the distance from the center of the bars to the bottom fiber. That's my cover. Okay. Now, there are different covers that you'll talk about when we get into the detailing. There's a side cover, and then there would be top cover for steel in the top region. But when you see the term bottom cover, that's just this distance right there. And we're saying that for this one, that's 1.5 inches. Okay. And then the reinforcing that we've chosen to look at is 3 number 8 bars. So all you have to do on a beam like this, I've got my gross dimensions, H wide is my B, my height is 20 inches. And so you got to kind of watch, whenever a problem is specified for you, are you given the overall depth or are you given the D value? I need D, but in this case, I gave you H. So you've got to correct this guy to get this 1.5 inch cover included. So my D on this will be from here to here. So it's going to be 20 minus 1.5. So that's the first thing you got to figure out. We then calculate the rho. And with rho and my n, I can then get my k, and then if I have k, I can get kd, and then we're back to just being able to plug and chug and get my and phi. It's a very, very simple process as you start to kind of work through it. So again, my students, you guys will work on these actual calculations yourselves. So in this video, we're going to turn our attention to calculating that third point. If you remember in the last video, we were looking at the moment curvature relationships for a beam, and we kind of defined how you can find those 3 points that exist on a basic moment curvature relationship. And I'll toss this back up so you can kind of see that as we're looking at SRR beams with strain diagrams and this linear relationship, okay, the overall behavior of a beam generally looks something kind of like this. And where the first region was our cracking point, the second one was our yield point, and then we have some ultimate that lives out at the end of the life of the beam. Okay, and so in our last video, we talked about how to figure out where this point was on cracking and then where this point was on our steel yielding. This video, we're going to be looking at figuring out where is that point, okay, and what's our corresponding moment and our corresponding curvature related to that. And so that's the purpose of this video, okay. All right. Now, before we do this, I'm going to show you, we're going to kind of take a side step here real quick, and we're going to define a very special strain condition. Remember when we did the yielding strain diagram on our picture, when we were looking at this, we were looking at the case where epsilon S was equal to epsilon Y, and then there's some corresponding concrete strain. Now, if you remember from our concrete materials video, we defined the ultimate strain in concrete as being the point at which we hit 0.003. That basically crushing occurs after that point, okay, and that's what we're call as our epsilon CU. Okay, we're going to define a very special, unique condition in which we call it the balanced strain condition. Okay, and that's a strain condition that would exist, for a given curvature at which my strain in my steel reaches its yield value. So this is for FY 60 KSI, that would be epsilon Y, that I reach my yielded value in the steel at the exact instant that I reach a strain of 0.003. Now, this is a highly theoretical point. This may or may not happen for a given beam, okay? But it kind of gives us, if I can calculate this, I can do some things where I can evaluate, my condition of, do I yield the steel or do I yield or fail the concrete first by comparing off of this value, okay? And so this balanced strain condition, while it doesn't have a whole lot of meaning relative to today's ACI 318 code in yesteryear, I sound like an old guy now, in older versions of it, this was the starting point, okay? And they would ensure ductility by calculating this balanced strain condition and then only taking, setting your reinforcement ratio off of that value, okay? And so that's kind of one of the approaches that we had. So if you look at, like we said, for any given beam, we may or may not be able to figure this out, but it is a very useful factor to have, okay? And we'll use it as a basis for comparison. Now, if you remember, we defined a reinforcement ratio as being the reinforcement ratio as ASBD. So now we're going to define a balanced ratio in which this becomes rho B, and this is the amount of steel required to get us to the balanced condition, all right? Because again, that's the only variable I have in this. I'm prescribing epsilon CU as 0.003. This guy, the strain, I can only get that by varying the area. Okay, so we're going to define rho then as AS over BD, where AS is some area of steel. All right. So that's kind of the definition of a balanced strain condition. We'll come back around to that here in a little bit. Okay, so let's get in and let's start talking about what the ultimate strength looks like. Once we get past cracking, if you remember, we had a strain diagram that we said that, when plane sections were in plane, I had a linear relationship that existed in this, where, again, for a rectangular section on this, here's my strain in my steel, this is my strain in concrete, they're separated by a distance d, and we're going to define the location of the neutral axis as a new variable c. Okay, now, we've called it KD when it was uncracked, we called it X when we were looking to find the yield point. C is now the corresponding location of the neutral axis as we start moving into ultimate. But what happens is remember, now we're starting to put the prescription that this guy is 0.003, okay, the limit of the strain at the top of this thing. And if you remember from our material research, we said that as we get up to strains higher than about 0.002, we start to end up with a relationship that, the stress in the concrete corresponding to this strain, 0.003 is different than, let's say that, down here was the 0.002 strain. Well, I have a higher stress possible on that, okay? Because remember, our basic, if I plot strain and I plot stress for concrete, it was a curve that kind of looked something kind of like that, right? And where this was my ultimate and this was my maximum, that curve, it's different, okay? And it's no longer whether I'm here or here or here, the relationship between sigma and E no longer follows Hooke's law. It's not the same value, because if E is constant, we violate this. So you kind of look at this picture, it's kind of a mirror image, and that's what we're getting. And so my peak stress in the concrete beam does not occur where the peak strain is, it occurs somewhere else. And so I get this non-linear function for the stress. And this is a huge deal, because now Hooke's law, which was one of our earlier assumptions of LEIH, no longer works. And so we've got to be very, very careful on this, but we can kind of start to plot this. I do know that a zero stress and a zero strain, those are the same point, but basically this becomes my stress block. And so in order to play that same game whereby, we came in and, if I call that as C-res, to be able to find C-res when comparing to T-res, that was a major issue. Okay, and so we want to look at, how do I calculate this? Well, if I know the characteristics of this and I know C, I could do an integral and come up with an approach to find C res, and then I could find the centroid of that C res as some, beta parameter, which is a multiple of C, to locate where this is. It's no longer 1/3 because it's not triangular, and it's not a half because it's not uniform. So we want to come up with an approach to be able to kind of calculate this. But the biggest idea when we're calculating the ultimate strength is that Hooke's law is no longer valid for us. So we've got to come up with another approach to being able to find that. All right. So if we kind of look at this, okay, we can start to kind of set ourselves up for some basic relationships. I do want to point out then that if I call this as beta C, then we're going to define a distance. In this particular diagram, they call it Z, but it's basically the depth minus this beta C character on this. All right, so let's define a couple of constants as we start to kind of look at this. Okay, if we define a couple of parameters in this, okay, we can now compute the nominal moment through these parameterized formulas that if f prime c is less than 4,000, we're going to take alpha as 0.72. If f prime c is greater than 8,000, it's 0.56, and then there's a linear interpolation that exists in between these. Okay, and so I can plot this alpha curve that looks something kind of like that. And I'll explain what we're going to do with alpha and beta here in a second. Okay, and so we can plot all of these as functions of f prime c. All right, and so there's my alpha of 0.72, here's my alpha of 0.56, and then we get that linear interpolation that exists in between those, and then f prime c is across the axis on the bottom. In a similar fashion, we'll define beta then as 0.425 when f prime c is less than 4,000, and 0.325 when it's greater than 8,000, and then again, a linear interpolation in between gets me a function that looks like this one. Here's my constant, slope, another constant. Pretty easy for us on the end. Okay, and so what they found from experiments is that those parameters alpha and beta do a pretty good job of approximating the ultimate stress distribution of this. Okay, and so what will happen is that from those two parameters, I can estimate the nominal moment as simply being rho, my reinforcement ratio, times Fy, because again, we're looking to yield the stress in the steel, times BD squared, okay, and then multiplied by 1 minus beta Fy rho all over alpha F prime C. It's not an overly, it's a complex formula and it's not hard to calculate, but it's a little cumbersome and it's not real friendly, okay? It's effective, but we really need to find a better way. And so this is what leads us into, one of the biggest techniques in the world of concrete and steel design. All right. Let's see. Okay, and that will be the purpose of our next video. Right? Okay, so that's all we want to do is just kind of get a little bit of our curvature relationship and start to kind of calculate these nominal moments. And we'll show you a much faster technique next time called the Whitney stress block in our next video. So anyway, I know this one was a little bit short, but we'll go from there. And, as always, kind of, if you understand the strain conditions and what we can kind of do with this, please, leave us some feedback on the videos, and we will talk to you all next time. Thanks for tuning in. Happy engineering.